Well, hello everyone. Welcome to this webinar. I think we just wait another like half a minute to give everyone the chance to log in, and then we will start with an introduction by Martin Peacock from Zimmer and Peacock. So just a few more seconds. So I'm just talking so you all guys you can hear that your audio works properly. And yes, so I think, please, Martin, just take it away.
Thank you very much, Lutz. Well, welcome everyone to the first webinar from ZP and PalmSens. PalmSens, I think PalmSens is a better name than PalmSens, but no, welcome. So this has been a long time coming. I've been watching and aware of PalmSens for over a decade now, and I would almost say 15 years, getting close to. I saw the first sort of handheld potentiostat from PalmSens a long time ago. I was living in California at the time, and I thought, this is perfect. So I'm really delighted now to be finally teaming up with the guys to do a webinar. So, you know, over the years, when you look at, let's say, the PalmSens potentiostats, they've got smaller and smaller. And now, obviously, they've been cutting edge again, and now they've brought it down to connect straight to the Android phone. So they've really, you know, if I see another LinkedIn post where somebody's showing the testing on an Android and it's a Sensit potentiostat, I think the investment community is all going crazy, thinking this is great. But us who are all in the know, we know what's going on here. They're all just buying Sensit potentiostats. So yeah, we're really delighted to be teamed up with the guys this afternoon. What's going to happen in a bit? Professor Lutz is going to present on glucose sensing. He's going to give you the theory behind it, and then we're going to do a quick transition over to Solren and Motz, who are in our conference room in Norway. So I think at the moment we're basically coming in from the UK, from the PalmSens headquarters, and from the ZP headquarters. So it's a sort of, you know, three center webinar. So I won't say much more, but I am looking forward to this, and I'll hand back to Lutz. So take it away, Lutz.
Yeah, hi. So I'm Lutz Stratmann. I'm with PalmSens. I'm an electrochemist at PalmSens, and yeah, today I'm going to present to you well, the principles and theories of the experiment that we're going to do today, so the glucose measurement. And I brought with me Adi today, my coworker, who is your voice at the chat. So yeah, don't hesitate if you have questions, just to write into the chat, that we can answer your questions later during the Q&A session, which will be after the experiment. Okay, cool. So let's just dive right into the experiment. So today we want to detect glucose, and how are we going to do that? Well, what is the chemical reaction? We're going to take glucose, and we're going to oxidate it. So we're using, in this case, oxygen to oxidating it. And that is done with the enzyme glucose oxidase. Well, as chemists, biochemists, we're trying to be systematic and not rather creative with names. So glucose oxidase is an enzyme that oxidases glucose. It oxidases the glucose to gluconolactone, which is not very stable in water. Usually it decays immediately to gluconic acid. That makes it not great for detection, and it also doesn't have like a lot of electrochemical detections. And today, well, we want to do electrochemistry. Fortunately, a byproduct of the glucose oxidation is hydrogen peroxide. And the hydrogen peroxide can be detected at an electrode easily and being reduced to oxygen. That oxygen can, in theory, again react with glucose. So we would have to have a cycle. This is now all a bit abstract. If you like it a bit more, well, I like it a bit more cartoon-like, that you can have a better visualization of the reaction. So here now you see in green the reduced forms of the different species, and in red the oxidized form. You see how glucose is oxidized to gluconolactone, and it does that with the enzyme gluconeoxidase. Enzymes do have an active center. That is the place where the actual reaction is happening. And that active center is before the reaction in its oxidized state, and then it takes up an electron from the glucose, so the glucose gets oxidized because it loses an electron, and the active center gets reduced because it takes up an electron. Right, but enzymes are catalysts. That means they make reactions easier, but in the end, they look the same as before. So now that active center needs to get rid of that electron, and it likes to use oxygen for that. So the oxygen is taking up the electron from the active center and is turning into hydrogen peroxide. Okay, so I've not done like the complete proper stoichiometric reaction. This is just to give you an idea what's going to happen, right? And the hydrogen peroxide is then again oxidized at the electrode. Okay, so this is what's going to happen, and we're going to do that at an electrode. And now you think like, oh, that sounds rather complicated. We need a lot of stuff for that, right? Well, actually, you don't need a lot of things to do an electrochemical detection. You need, well, your solution with your sample in it. Then you need electrodes, so the interface between the liquid and the solid state, right? Usually a metal or maybe a carbon species. And in our case, because we want to detect the glucose with the glucose oxidase, our electrode needs to have glucose oxidase on it. Well, we're using a Zimmer and Peacock electrode for that. That already has glucose oxidase modified on it. And now this electrode needs to have a potential applied to it, so we can convert the hydrogen peroxide and measure the current that indicates that the reaction is happening. For that, we need a potentiostat, and we need a software that controls that potentiostat, and accordingly some kind of computer, or in our case, a smartphone. And you see on the left side the abstract concept, and on the right side the actual setup of the experiment. And the upper part, so the software and the potentiostat, this is what PalmSens does, right? So you see the smartphone with our app PS Touch that you can use for doing your measurement. And you see the Sensit Smart, a very small potentiostat to perform the measurement. The lower side, that's, let's say, is closer to the reaction. So like what are the solutions that you use, how to make a proper electrode, have a protocol to run the measurement. This is all what Zimmer and Peacock are very good at. So you immediately see why we're doing this together, because we give the two parts that you need for your electrochemical detection. So just to give you a short idea of what is that little black box that we're using here, that is the Sensit Smart. So it's a very small potentiostat based on the Amstead Pico, which is an OEM module. That means this is a small potentiostat that you can build into your own devices if you want to build something yourself. In this case, we built it into our own device, which is the Sensit Smart. So an end-user device that does the usual electrochemical techniques like cyclic voltammetry, square wave voltammetry, chronoamperometry, electrochemical impedance spectroscopy, and it is compatible with PS Touch for Android. All right. Yes, so now I will just tell you what settings you can do. That's a bit easier on the big screen, or what settings we do for this experiment. That's a bit easier on this big screen. And then I will transfer over to Solrun, and that she can show you the experiment. Okay, so for this experiment, we're using the technique chronoamperometry, which just means we're applying a constant potential over time and measure the current. The current ranges that we select, which define like how sensitive is your potentiostat, or what resolution it has for the different currents, that we use the current ranges between 1 nanoampere up to 10 microamperes. And the advantage of most of our potentiostats is that they have auto-ranging. That means they will choose the right current range in the range that you have set for you. Then we have the equilibration time. That is 5 seconds. That is just a short waiting time that the potentiostat has before it really starts to record the values. This is because at the beginning of such experiments, we have often high capacitive charging currents, and we don't want these. We want to see the electrochemistry and not the physics. We apply a constant potential of 650 millivolts. There you can oxidize the hydrogen peroxide nicely again. Then we have an interval time of half a second. That means every half a second we will record a value. And then we have a running time of 600 seconds. That can be longer as well. That's no problem. Usually what people do for these type of measurements, they set a time where they definitely know their experiment will be over. And then when they have all the values earlier than they expect, they just stop the measurement and save what they already have. Okay, this is all like what the theory that we want to do today right now, that you're like feel ready for the experiment, because we want to get into the action. So I just would like to transfer now to Solran, who will show you this experiment.
Hi, so my name is Solran, as Liz said. I'm a scientist here at ZP Peacock. And today I will demonstrate for you how you can detect glucose in Coca-Cola. So what we need is the Sensit Smart from PalmSens. And we will insert that into our smartphone and access the PS Touch app that you can get from the App Store. We will use the glucose sensor kit from ZP Peacock. And here are some glucose sensors. We will insert that into our Sensit Smart, like that. And then we will go to Method, and we will put the same parameters that Lutz showed us. So 0.65 volts, 600 seconds, well, interval can be 0.5, and that's good. Then we'll go to the plot, and we will start with the Coca-Cola Zero.
So it's just worth saying that we're going to do essentially two experiments. We're going to start with Coca-Cola Zero, which is obviously in some countries the Diet Coke, the sort of zero glucose version, and then Solran will explain that we'll go to Coke with all the good stuff in it, with all that sugar in it, and we'll obviously have a look at the difference in the signal. So it's essentially, I mean, as Solran sets this up, it's a glucose sensor. It's plugged obviously into that Sensit Smart. The Sensit is going to apply the voltage. As Solran places it into the Coca-Cola Zero, then she'll start running the experiment now, and Solran can talk us through that. Tell me when you're ready, Solran.
Yeah, so I just started the experiment. So we will see a curve forming. So what you see now is a typical chronoampermetric curve. This is called the wetting time. We're waiting for a baseline to form, and now it creates a electrical double layer, and diffusion is happening. So when we will reach equilibrium, that's when we will have our baseline, and that's when we will swap solutions. So as Lutz and Martin said, the Sensit Smart is a potentiostat, so we can use that for several molecules. Like, for instance, at ZP Peacock, we have sensors for potassium or sodium, nitrate, lactate, etc. And it's only your imagination that limits what molecule that we can detect with the potentiostat like this.
So I might just add, so the sensor that we're testing at the moment is really what they call a CGM, a continuous glucose sort of monitoring sensor. So this is, as Lutz said in his presentation, the enzyme is actually immobilized within a polymer. So with that kind of sensor, it takes a little while for the signal to essentially come down to a baseline. There's another version of glucose sensing, which is SMBG, self-monitoring blood glucose. And those sensors, you put a drop of blood on and you get results in 5 seconds. And that's because everything is soluble. It all dissolves up into the blood. You get this instantaneous reaction. But the downside is you can't reuse the sensor. So if you want to do continuous monitoring, then you want to do CGM. So we wait for the polymers to wet, and when it's reached a baseline, then we can then essentially transfer it across to the real Coke, let's say, and have a look at the glucose signal then. So it's a bit like watching paint dry, the scientific version of watching paint dry. But Solron, tell us what you're seeing.
Okay, now it's slowly forming a baseline. So you can here see the curve, and yeah, it's stabilizing. So we can try to swap solutions now.
Are you tempted to swap now, or do you want to wait a few more seconds, or do you feel how many seconds has it been?
Now it is 160 seconds. So we'll actually.
Yeah, go on. Sorry, Soren, go ahead.
No, we'll try to swap the solution now. It would get more stable with time though, but I think this will be sufficient. So we will swap solutions like that. Okay. And now you see that here is the baseline from the Coca-Cola Zero. And here you see a clear signal that we have sugar, because the current has increased. And now that you can see that it's like flattening out. And eventually it will start decreasing a little bit, and that's just because we don't have stirring. So there's a depletion of glucose at the electrode. But what you can see here is a clear step from Coca-Cola Zero to Coca-Cola with glucose in it. So
that little dip, I noticed you just, as you did the swap over, I just noticed you just knocked the electrode, and that kind of broke the electrical connection. So it did that little drop out, but as you say, then it is now coming back to a nice little plateau. So cool.
Yeah.
And I think we should watch it for a bit because it's quite nice. So we have we have that, as you say, as you described, we have that settling time. Then we have the little dip where we were transferring from one beaker to the other beaker, and then it comes back up. And if you look now, it's coming to it's rather than falling now, it's essentially at a plateau. And it's essentially showing a steady state current due to the glucose reaction with the enzyme. So what are your thoughts, Solron?
Well, I actually stopped the measurement right now, but yeah, you can clearly see the step as the electrode or the sensor is detecting glucose. And as you said, it's slowly starting to go down due to the lack of stirring, but I would say that this is a very successful attempt at detecting glucose in the Coca-Cola.
So I think it's so I appreciate the nice introduction from Lutz. So we got the nice theory from Lutz, and then essentially we presented then the demonstration of that theory in that Sensit smart potentiostat along with our glucose sensor. So I think the next intention was to maybe ask questions. So there's a bit of a chat window up, but Ardy, you also had the idea of putting a few polls out there. So do you want to just tell us about the polls that you had, that you were thinking about?
Yeah, sure. So the idea is that everyone can write a question below here. And actually, I got some questions in a private chat window, so I'll ask that to you both as well. But please, guys, if you have any questions, just drop them in the chat. Let's start with the first question. This one is for you, actually, Martin. Actually, you showed something with glucose, of course. It's nice that it works, but what if you want to do any other analyze? What is possible? Could you explain a bit more about that?
Yeah, I mean, what's possible is this. I mean, the smallest analytes around are probably ions. So if you want to do the smallest analyte is probably the proton. So with this Sensit Smart, you can do pH. So that's the smallest thing you can do. Then you come into small molecules like glucose. So with those, you then need things like enzymes. So there's a glucose sensor out there. There's a lactate sensor out there. There's an alcohol sensor out there. There's now a cortisol sensor, which is a hormone. So we like, with small molecules, we like it if they have an enzyme. And then you're starting to go a little bit bigger. So proteins. So everyone's very interested in really immunosensors. And immunosensors are sort of the next level in difficulty, but we can do proteins. And I say we, I mean you, people out there. And then the next level after the proteins is then maybe the viruses. So, we've done some work in the last year, and it's in hospitals now for COVID-19 detection. And then the next level up after that then is bacteria. So we can do bacteria. And I think probably the largest thing that we are detecting at the moment is sperm. So we're measuring male fertility. So I just given you a range from the proton up to spermazoa.
Yeah, thank you. We also have a question for Lutz. Lutz, you and Zoin, you actually showed a very small potential stat, right? The Sensit Smart. But what instrument would you recommend, and how do I know if this Sensit Smart will be good enough for my sensor?
Right. Okay. That is a bit of a difficult question because there's so many different types of experiments out there, and especially when you want to commercialize them, there are even more questions popping up. So in general, I would say when you start with researching your technology, you should have a rough idea what kind of potentials and currents you're looking at, right? And then you will have different potentiostats. I mean, that depends on your research. I guess because of the title of the seminar, nobody from like car batteries or giant fuel cells is here. And they don't, they have very large amperes. So they will look for very different devices than what we offer. So we offer usually small devices. And these small devices have lower currents, lower potentials than these super big ones. But even in this range of potentiostats, there is a difference. For example, we have the PalmSens 4, which can go up to 30 milliampere, while a potentiostat of the size of the Sensit Smart can go up to 3 milliampere. So this is one criteria. How much current do you expect? Then how much resolution would you require? Like how low do you go in current? And then you would look at that parameter as well. Then what potentials you need to apply, etc. Which technique do you require? So we have, of course, every producer has this, and we have that on our website documents where you can look at the different specifications. And usually you first look like, okay, I think if I would say like the main things are the current that I expect, the potential that I need to apply or expect, and then the technique. And that will be like the 4 main rough criteria. You look for a potentiostat, and then you go to other things. Let's say for all these type of portable applications, we do have a lot of portable potentiostats. But when you want to go into larger scaling, you usually want to build your own device, that has your own brand, your own shape, right? We all want to have, because we've talked about Coca-Cola in that seminar, we all want to have a product that is as iconic as a Coca-Cola bottle, right? You see the shape and you know which company it is. You have an association with it. So you want to have these OEM products where you buy just the PCB, like the Amstead Pico module, and you build your own device around it. So usually when you want to go into that commercial direction, I would advise that you look like which ones of these is more suitable for you. So in most cases, it's a bit of an individual process, but you can usually already narrow it down. And the advantage, like when you work with a company like PalmSens, is you can start with research potentiostats, and often you can use a research potentiostat that also has an OEM version. So you don't have that strong gap in your transition process from research to OEM. So when you do your research, you do it with the same potentiostat that you then later use for serial production. I hope that gives the person an idea.
Let me ask you a quick question.
Yes.
What's the top of the range single channel EIS instrument that you have?
For us, that is the PalmSens 4, which is also the biggest one. Right now,
But the answer to the question is, it's the PalmSens 4 that you want. because that will give you EIS and all the DC techniques, and probably has a fairly good current, low current range. I know who's asked the question, so I'm going to answer the question. It's the PalmSens 4.
Okay, yeah, it is
It
like
wasn't me, but I know who was asking the question, so the answer is PalmSens 4.
okay, because the PalmSens 4 is also like, for us, that's the most versatile one. So that's like when people are in doubt which potentioset, we usually recommend the PalmSens 4. Because it is like it has the highest specifications of our instruments, and it will most likely cover everything. If somebody wants to go into serial production of their own detection system, like system similar to your chili pot, for example, if you want to make, or a COVID detection, you want to rather have something like the MSTED Pico. But then you have to check for your specifications, because the smaller your potentiostat, also the narrower the capabilities, you could say. So then you want to check it, and you want to look at the core specifications.
All right, thank you, Lutz. And we actually have 2 more questions from Martin. Martin, we just saw this experiment with the Simran Pico biosensor. How many measurements can we do with this one?
I can answer the question in a slightly different way. We have now been running one of these glucose sensors in one of our projects for over 3 months. So that's a slightly different answer. But we've had one of these glucose sensors in continuous operation for over 3 months. Now your question is how many times can I reuse it? And I'll answer the question by, depends how much care you take over it. But in continuous operation, these sensors have, in our hands, and we are pretty expert, have been used for over 3 months. I suspect that we'll be able to take these glucose sensors to 12 months quite easily. And the reason that we're doing this is we've got a program for measuring the health of fish. You know, fish are our cousins. We've got to take care of these fish. You know, so we've got a project which is the continuous monitoring of fish and the health of fish. And in that project, so far, we've been continually running the glucose sensor for over 3 months. So that in part answers your question. Now, if you put blood and urine and all sorts of yuck over it, then you've got to basically decontaminate it and then reuse it. So the answer to your question is they're pretty robust, but in the end, they're as robust as how robust they are depends on how well you treat them.
All right, thank you. And we also saw that the experiment it takes a few minutes. What if we would make this experiment a bit faster? What would you need to change?
If we were going to try and change it, so if your application is put a drop of blood on there and get a fast reading, then rather than having the enzymes all bound up in a polymer, so we've put them in a polymer so they essentially don't dissolve away, that they're locked in place. Rather than doing that, we would make what's called a soluble formulation, so the enzyme quickly, the blood came in, the enzyme dissolved, the reaction started immediately, and we could do a fast result. So that's how we would speed it up, either make the reagent soluble or very much thin down the polymer that we were actually using.
All right, that makes sense. Another question, and I think this is best for Solwyn. So when you did your experiment, and how exactly do you now know the concentration of the glucose? And what is actually the accuracy if you compare it to other analytical methods?
So I think if Solrun's not there, I'll quickly answer the question.
Yeah, sure.
So essentially, now what comes off that potentiostat is a current. So what you have to do is you have to have calibrated the batch of sensors to say, I have a sensitivity factor that says this current equals this much glucose. So what the Sensit Smart does is it gives you the raw signal. Now, Lutz touched upon the fact that they do an OEM product. So you really then have to do the next piece of engineering, which is take the raw signal, put it through your calibration factor, which is based on your factory calibration of the electrodes, and turn current back into glucose concentration. So there's a step that we didn't show you today, but we've shown you how to get the raw current. Your next step then is to apply a calibration factor to turn current back into concentration. And that's how you would get the glucose reading. I just want to say, I mean, there's no electrochemistry, the accuracy of a commercial glucose strip, and these are accepted in hospitals, accepted across the world. at about 90 milligrams per deciliter or 5 millimolar, those glucose strips are only plus or minus 15% accurate. So it's quite, inaccurate, but it's good enough for the application. So the accuracy you require depends on the application that you're dealing with.
I have actually a question for Martin. So I have a question for Martin. So because I was listening to your fish project, and I was wondering, there's a big problem usually in so long continuous measurings, and that's like biofouling. Did you somehow take care of it, or is the fish tank just so clean that you don't have like something growing on the biosensor?
It's a good question. So biofouling, the further you go into the body, the less problems you have with biofouling, because biofouling and foreign body response, which you're describing, is, if you're making a interstitial glucose sensor that goes through the skin, then this zone of your body is very good at foreign body rejection, because that's where you get all splinters and cuts, and that's where your immune system. If you put the same glucose sensor much deeper into the body, it doesn't actually get fouled at anywhere near the same rate, because your immune system is actually most responsive at the sort of peripherals of your body, and the deeper you go in. So in fact, where you place the sensor, if you go in quite deep, then you actually get away from some of the biofouling problems. And the quick answer is no, we don't have a magic bullet where biofouling just gone away now. But that is the biggest problem in continuous glucose monitoring in human beings, is biofouling. We can partly overcome it because we can go quite deep in the fish, whereas with a real human body, you don't want to be that invasive just to overcome biofouling. So the quick answer is no silver bullet from us.
All right, thank you. I do want to launch the poll, and there is one more question. So let's first launch the poll. This is about what would you like to see in the next webinar. So of course there are several things we can show you. For sure we will have another webinar together with Zimmer and Peacock, and we would like to know what you guys would be interested in. And meanwhile, while you guys choose your answer, we're going to one more question. This is about, could you actually repeat the whole measurement? Well, I have good news for all of you. We're going to send you all an email with a link to the recording, so you can actually repeat it as many times as you would like, to just see what you were looking for. All right, and I see that meanwhile we get lots of responses to what would be the next webinar. I see that number 1 is currently to measure pH and to measure actually caffeine. Yes, of course. Right.
I see all these people buying them, and then they're measuring if the colleagues in the office have replaced the coffee with decaffeinated coffee, or replaced the decaffeinated with caffeinated coffee, to just create a bit of drama in the office.
I think it says something about the technique of electrochemistry that you can actually deal with. You can test Coke. Coke's a fairly clean sample. You can test blood. You can test white wine. You can test red wine. You can test orange juice. You can test coffee. A lot of analytical techniques like fluorescence or absorption spectroscopy, they demand that the sample is kind of transparent. Whereas electrochemistry, you can test things from blood to chili sauce, and that's really why I think if you want to make a low-cost, real-world sample test, then I think electrochemistry is the guy. If you want to make a laboratory test that sits in a big centralized hospital with lots of air conditioning and lots of control of the conditions, you can need electrochemistry. You could use all sorts of techniques like surface plasma resonance. But if you want to make quick and dirty tests at a low cost, then I would recommend electrochemistry.
All right. Well, we're done with all the questions. We've answered all of them, and I hope in a sufficient and pleasant way. We also see clearly that to measure caffeine is the most popular one, so we will think about how we can organize a webinar around that. And for sure, we will invite you for that one as well. And for now, I would like to thank everyone for joining, and I hope you've enjoyed this webinar. All right. See you guys. Bye-bye.
Cheers. Thanks, Ardy.
Bye-bye.
Thanks, guys.
Thank you, everyone, for watching.